as we go through different functions. So before we get started, I always want to highlight, just in case somebody hasn't watched the previous videos, this paper. And I highlight it over and over again because it does an exceptional job about overviewing the process of modeling species distributions. It's all in one place, and it talks about all the kinds of things that you might want to consider when you're doing these kinds of models. So I don't want to go through all the different kinds of models again. We won't talk about geographic models in this module. They're fairly simple and easy to do within the coding environment. You can also find examples of code if you run a model within EcoCommons and look at the code. So geographic models, fairly simple. Similarly, profile models are not terribly complex, a little more complex than geographic, but we're just doing things in environmental space instead of geographic space. And so we will be talking quite a bit about some of the statistical models. Be showing you a couple of real brief examples of a binomial GLM and a generalized additive model for when those relationships between your predictors and your response are not linear. And again, the statistical models are really good for inference. They can be really good for prediction if you have good data feeding them, or if you have a really good understanding of the system that you're modeling. And you need a response variable. You need presence absence data or abundance data, something like that. So we'll go over a couple of examples in R on these guys, and we'll go through a couple of examples on the machine learning algorithms, which do a fantastic job of soaking up all the deviance in your training data. You can overpredict using these models, and you can guard against that in a number of ways, but one of the primary ways that you can catch it is with really good validation methods, which we'll talk about in the next module. But today we're going to talk about primarily Maxent. So that's a model that can use presence-only data. So most biodiversity data doesn't actually have background points. But in our first module on occurrence data, we talked about some other ways that you might generate pseudo-absence points. So that gives you the kind of response variable, a binary response variable in that case, where you can run things like boosted regression trees. So we'll be talking about those two examples, how to do those in the code in the R environment. And again, usually these models are really good at predicting. And just to go into a little bit more of the differences between these models. Again, machine learning methods like Maxent have been around for a long time. They're really well tested. There's some really good understandings of how to use them. Similarly, random forest and boosted regression trees are very similar methods and produce good predictions generally. Boosted regression trees can, because they, especially if you use the GBM step option within the Dismo package, they'll focus in on those areas where, so they're doing boosting in areas, environmental space where they're doing poorly. So that can produce better predictions. It can also overfit the data if you're not careful. But there's some good ways to tune boosted regression trees, and that's one reason we focus on them. So Jane Elith and others have done some really great work on how to get more out of these models. We're just going to touch on that in this example. And artificial neural networks tend not to do as well as random forests in most examples. They're great for really complex prediction problems, but often we're not as our variables are not as complex. We don't understand the interactions between all the nodes and other things that are in an ANN. But it's an area of active research, and it's something you could explore further. But today, we'll just be talking about model fitting in these examples. And when you're fitting a species distribution model, just like when you're fitting any basic statistical model, it's not a bad idea to reduce multicollinearity, right? So that just means your predictor variables are highly correlated to one another. If that's the case, you really can't say much about your parameter estimates, so you can't determine how influential one variable was over another because it could be either one because they're highly correlated to each other. You don't necessarily need to drop correlated variables from some of the machine learning methods. You certainly need to do it in statistical methods. But for machine learning, when the goal is just to predict, sometimes you can get away with multicollinearity. But generally in ecology, you want to be able to interpret the model a little bit, even if you're running a machine learning algorithm. So it makes sense to go ahead and take care of, reduce the highly correlated variables. So you remove unimportant or highly correlated variables, and you try and keep the model as simple as possible, but no simpler. So the simpler the model is, the more easy it is to explain it and understand it. And there's a penalty for complexity. Often as you get more complex, you tend to overpredict. So usually a simpler model, a parsimonious model, is a little bit better. And there's so many decisions that you make during the modeling process. And we've highlighted a lot of those with the occurrence data, with the environmental data. And here there's going to be more things that you can choose in the model fitting. You can choose all kinds of arguments for these algorithms. And some of those arguments are going to make sense for the model that you're running. And I would encourage you again to read the literature, understand how similar species in a similar region have been modeled already, what's worked and why, and make decisions around setting those arguments. Often the default arguments do pretty well, but generally if you really want to dig in, you want to really understand what's worked well in similar problems for similar species. Generally, averaging model results gives you a better result. So that can be true if you're modeling across time. If you average a bunch of daily predictions, if you have enough data to do that, you're going to get a better result than if you average the variables first and then just generate one model for those averaged variables. You're dulling the signal in the data if you don't average those predictions across time, for example. But also across algorithms, it can work really well. So ensemble modeling, often if you're really not sure which one works better, ensemble modeling is a good way to go. So those are just some initial thoughts on model fitting. But I also want to highlight, one of the outputs of your model fitting exercise is often what people want is, well, I want a map that shows me where this species is present and where that species is likely to be absent. Clearly, that's an oversimplification of the output that you get from a species distribution model. Most of these correlative models are going to give you a probability between 0 and 1. And there might be all kinds of values across that span of numbers. But you want to choose a threshold that will correctly select those places that are most likely to be suitable habitat and where your species is likely to be present and where those species are more likely to be absent. So thresholding is deciding on one threshold where everything above that number is going to be deemed as probably suitable to be present, and everything under that number is going to be suitable to be absent. 0.5 is the obvious threshold, but there's all kinds of examples in the literature where that's often, almost always, not the optimal threshold to choose. So we'll talk a little bit about that in this section, and more in it about this in the next module on model evaluation. But in this section for the R part of model fitting, we're just going to go through a few examples. So we're going to go through a Maxent example, a BRT example. We're going to touch on some of the things that Elith et al. Have done regarding tuning your boosted regression trees. I'm also going to highlight GLM, which I forgot to write down here, and a GAN. So sort of your basic staples. These are probably the most common models that are run to generate species distribution models. Mars is also becoming more popular. But so the first step, if we're going to take care of multicollinearity, we want to understand how correlated are our variables. And I'm not going to get into the nuts and bolts of this function, but this is just a function that is going to create this panel. And in the lower part of the panel, we're going to have just the dots, or the data plotted against pairwise comparisons of your variables. And up in the top of your panel, you're going to get an indication of how correlated those variables are from 0 to 1. So this is the function that does that. And I'm then going to take my my predictor variables. So you remember from the last module, we created a stack of predictor variables. This is that stack of predictor variables. So it's all 6 variables in a stack. And we're going to select a bunch of random points from within that stack. So 1,000 of them. So across our extent, we've got 1,000 random locations that have been selected. We're then going to extract from that stack of data the random point location. We're going to extract the environmental values from our stack using those random points that we generated above. So essentially, for each random point, it's going to fall somewhere in our study area, and then there's going to be 6 environmental variables that are going to be pulled out from the stack. So you're going to get a column for each environmental variable for each random point. So essentially, it gives you a nice, quick data frame, and then we can look at the pairwise comparisons, the correlation of that, using this function. And so these are our environmental variables, and you can see that in this case, actually, this is a marine example. This is something I drew from somewhere else, but so this is sea surface temperature and bathymetry, and they're not super correlated, but 0.45, so that's probably not something we need to worry about. I haven't looked at the correlation matrix from this work in a while. I don't think there was anything too alarming in it. Oh no, that's not true. So I've just looked at it again, the latest, and wetland connectivity and AWAP were almost identical. So a correlation of 1.0. So you definitely want to drop one of those 2 variables. Anyway, that's I think that would have been a little lower if we'd increased the number of random points that we were looking at. But anyway, that's a strong correlation. And you'll see that in the results of your script. So the next step is sort of in fitting our model is to identify, well, what presence data are we going to use? We also show an example of setting a mask and setting an extent. Those are used in some functions, not necessarily the ones we're showing here, but it just shows you an easy way to do it. So, and you saw this in the previous modules, but we're just going to create a spatial points layer, and we're going to do that from the latitude and longitude from those thinned data. So we're not using all of the this species of frogs data. Limnodynastes peroni, I think it is. We're just going to use the thinned out data as our presence data, and we're going to make that a spatial points layer. So we've seen that before, that's all we're doing here. And then to set a mask, we're just going to set a mask equal to the second raster in this stack of raster that is our environmental predictors. So we could have chosen any 1 through 6 here, but we chose 2 for no real reason. And we're also going to set the extent as the extent of this predictors stack. So those are 2 things that you might use later in some functions. And here we're going to show you how to just fit a Maxent model. And the Maxent model, so the default, if you don't specify how you're dealing with background data, you're just going to choose 10,000 random points for your background. So 10,000 random points from throughout your study area. And before you get started, it's a good idea to set your arguments. So Maxent args, and this is how you do it. You have to, make this list, and they have to be in quotes, and they have to be called this specific thing and equals true or equals whatever specified in the argument. So we've got a list of arguments that are used in Maxent. You can also find that online. But here we're just going to specify that we're removing duplicates. We're going to do some jackknifing to get at variable importance. We're going to plot the response curves, and we're going to generate some plots in the results folder. So those are the arguments that we're using. Probably the one of the arguments that's used more commonly, aside from these, would be one that relates to regularization. Essentially, if you pick a beta multiplier that has a bigger value, you're going to get more spread out predictions, essentially across geographic space. So that's probably the one that people play with most, aside from making sure they're getting the right plots and various things in their outputs. But anyway, this is the arguments. And this simple line of code is the machine learning algorithm. So this is going to run the machine learning algorithm. We're calling Maxent from Dismo. Again, that works because we have Java installed. We have the Dismo Java files downloaded. And then this is our predictor variables. So that's our stack of environmental data, right? This is our spatial points layer of the thinned frog data. And we haven't specified anything about background, so it's just going to assume we've got these 10,000 random points. Path equals is very fiddly, but here we're saying path equals results. So from our working directory, we've got a folder called results. And that is where a bunch of really cool results are going to be written. The plots that we've asked for, some variable importance plots based on the jackknife results, response curves, all of that stuff, plus a whole host of other things, are going to be written into this folder just by specifying this path argument. But this path argument can be pretty fiddly. So if it's not working, keep experimenting with your working directory and trying to get this folder called correctly. But essentially, once you do that, you get a lot of very interesting results that pop out automatically into this folder. And then we're calling those arguments as we specified above. And then the next step, if we want to make a map, is to take this model object. So that model object has all kinds of cool information on it. You can interrogate the model object in R as well if you want to. All kinds of interesting things that are stored directly in the model object. Your AUC values, your call, all kinds of things are there. And I'd encourage you to explore that. But if we use that model object and we use the predict function, and this is true of predict works pretty generically across most statistical and machine learning algorithms. So if you use predict your model object and then you tell it what data you're using, it will generate a bunch of predictions. So we're going to predict into that stack of environmental variables. So we're going to predict right across our study area to produce this map. And then we're going to plot those map predictions, and we're going to overlay the points that were used to generate those predictions on top. So that's our predictions with the darker shaded areas, higher probability of occurrence. And you can also create a map as a JPEG file and file it away in your folder. So wherever you specify. So here we're going to put it in the results folder. We're going to call it this name. So this, with the dev off at the end, this series of code just produces that map as a JPEG map that you can pop into your results folder. So I talked a little bit about thresholding. So there's all kinds of ways to generate a threshold probability of occurrence. And probably the most common one that's used in ecology is maximizing training sensitivity plus specificity. So we can actually pull that directly out of our results. And then we can use that threshold, and I can't remember what it was now. If you typed thresh in after this line, you get exactly what the threshold was. I can't remember what it was. But then what it's going to do is, again, we're going back to that reclassification thing that we've done multiple times now in the previous modules. But we're going to reclassify everything between 0 and that threshold as 0, and everything between that threshold and 1 as 1. And we turn that into a matrix, run the reclassification sort of function, which is in the raster package, and we're going to plot it. And you can see that there's a lot of places at this threshold, there's a lot of places where we'd predict the suitability for this frog is pretty good. And we might expect to find it in those areas. But we then pose the question, well, what if we wanted to be really sure where these frogs were? You know, we're going to spend a whole bunch of money on getting habitat put aside for these frogs. Where might those habitats be? So we want to use a much higher threshold than the one that's produced here. And the first step in this is, interestingly, the raw results, the raw predicted suitability don't scale from 0 to 1. So we're just going to rescale our predictions they're close to 0 to 1. I think they're around, 0.1 to 0.8 or something. But we're going to rescale those predictions so that they do scale between 0 and 1. So that's what this is doing. And it's creating a new raster with scaled values between 0 and 1. And then we're just going to say, well, everything that is higher than 0.8. So we're pretty sure that there's probably a frog there. We're going to put those places above 0.8 as a 1, and we're going to, again, generate that map. And look at how many fewer places we have that we're more sure we're going to find suitable habitat for these frogs and likely these frogs. Right? We have a much different map. And thresholding is, it's a science unto itself. There's lots of papers on it. Again, it really depends on what your question is and what your application might be on how you set these thresholds. I would do your homework and read some of the literature around the kinds of the reason you're trying to set that threshold so you can set it more optimally. And here I just want to highlight some other examples of, calling Maxent and either generating some cross-validation results or generating or using a bias data set or a bias layer to inform your background points. So this is the new arguments that we're going to use in this new function. And I won't go into all of these, but essentially the replicate type is cross-validate, and we're going to do 3 replicates. So that's essentially equivalent to doing a 3-fold cross-validation. So we're going to break our data up into 3 groups, run this model again. We're going to put the results in a different folder. And you'll notice there's 3 groups of results, 0, 1, and 2. So 3 groups of results that are produced in this folder. And you can see how different the results are with different data given to inform them. Now, that gives you a good understanding of how much is different sets of data influencing your results, right? If you're getting really different results when you do cross-validation, that should raise some alarm bells. You might not have very much data, but it also suggests that you have more uncertainty in your results than perhaps is suggested by the global model that you ran previously. So cross-validation is an excellent way to get an understanding of how much variation there is in your results. But interestingly, if I were to generate a really poor model, it didn't predict well at all, barely better than random, and I ran the exact same model again without cross-validation, because Maxent and the machine learning algorithms are using something called stochastic learning, you're going to get different results each time you run the same model with the same data, oftentimes. You're hoping that those differences between subsequent runs of the same model with the same data are giving you similar results, right? They shouldn't be very different. And sometimes they can be different if you run them on a different machine or a different processor. It totally depends on the algorithm and how things are set up. But some of these more complex algorithms that are being employed currently can give you slightly different results. If you have a really poor model, subsequent runs with the same data of the same model can produce really different results. So it pays to run these things more than once, multiple times, just to get a sense of, well, how stable are your predictions. But cross-validation does that even better. Right? It's an even better way to do that. now these lines of code, we're going to revisit that raster layer, the bias layer. So this is, we're going to load in that bias layer. So if you remember, that was created using a kernel density function in module 1. So it gives you a rough, the higher values in this bias layer are where there's been more sampling, and the lower values are places where there's been fewer surveys for frogs. And then we're going to create this background object, which is going to take the X and Y locations, so the lat and long, from this bias raster that we brought into our environment. And we're going to ignore things that have NA values, and we're going to select 10,000 points, just like you would expect with that's the default number of background points in Maxent. So we're still going to use the same default, but rather than just totally randomly selecting them, we're going to use the probability values within this bias raster to inform how likely it is we're going to select a given point. So this is indicating we're again going to ignore NA values, but we're more likely to select a background point in those areas with higher values. So in those places where more frog surveys have been done. So essentially we're trying to reflect in our background data the same kind of effort that went into creating our presence data. And then we're going to run that again using the similar arguments, but this time, so we're going to specify X equals, these are our environmental predictors. P equals, this is our presence data. That's our thin spatial points layer. And A equals BG. Those are all those locations that we've pulled out of by using the bias raster file to inform the probability of selecting any given grid cell. We're going to write this to yet another folder, and we're going to call on the arguments. And you don't get a hugely different result from the model without a bias layer. And you do get a little bit more along the coast of frog habitat, but generally it's not a huge difference. It's a fairly similar result. So using the bias layer in this instance and not using it. There are some cases where it will really transform your results. But now if we go to the idea of using targeted background or zero filling your data. So again, these are those locations where frog surveys have been done, but our target species was not found, right? So we're going to bring those in to our local environment, and using the lat and long from that file, we're going to create a spatial points layer. And then we're going to use that spatial points layer as our presence, or as our absence data, sorry. So these are the places where at least one survey was done, another frog was found, but not our target species. And when I initially ran these models, I ran them for all of Queensland, and then here I ran them for all of Eastern Australia, and here I've just ran them for Queensland. So the differences mean that we didn't have as many of these points to choose from when we ran this script. So ideally you'd want this number to be close to 10,000, but that wasn't the case here. So that was a lower number than 10,000 because I reduced the extent of the study area just so the models would run a little quicker for people. But anyway, when we look at those predictions, we can see that, hey, you know what, we're getting more possible suitability further away from the coast. So this is just demonstrating that, I mean, one, we had fewer background points to choose from than would be ideal, but also we're now able to discriminate more along the coast, and we're less sure about this area. So we're going to go ahead and the model is suggesting that those places that are environmentally similar might actually have frogs, whereas previous efforts didn't show that as much. So targeted background data has shown to have a profound effect on your results. And generally, independent validation has indicated that the results are better when you do this. So again, fortunately, there's a lot of independent data becoming available that you can use to validate your predictions. So you might get several predictions and you're really not sure what's best. That's certainly the case to now, right? We could look at AUC and just say, well, this is the one that produced the best AUC value. But really, you can't be too sure until you do that next validation step. This next example is looking to predict into the future, right? So we're going to list the files that are in this directory. So in that predictors future folder. So remember in module 1, we created a bunch of rasters that we gave the same names in both predictors and predictors future folders. And the predictors future folders had different environmental data in them, but had the same names. We're going to bring those rasters in, those same 6 rasters, but have different environmental future predictions. And we're going to stack them. So we're going to stack all of the rasters that are in this folder, predictors future. And then we're just going to use that model object that we've created up here, and we're going to predict into that raster stack. And this is the map that we're going to get. And we can see that it looks like there'll be a slight contraction in the amount of suitable habitat for this frog in the future. How sure are we of that? We'll talk about that in the next module. But certainly looks like in the future you might have fewer frogs around in Queensland. So now we're going to generate some pseudo absence data, and we want to be a little bit more sure about those pseudo absence locations. So we're only going to use grid cells that had 3 or more visits. So if there were 3 or more visits to a grid cell, we're going to, and they were looking for frogs, but they didn't find our target species, we're going to assume that's a 0. So in the previous run, we just assumed if one survey had been done in a grid cell and they hadn't been found, that was a 0. But now we're bumping that up to 3 visits. And you can see how we did that in the first module. But we're going to read those data in, and that'll be our 0 data. And then we're going to pull in that thin data. And we're going to make them eventually, we're going to bind them together and make them a data frame. So So we have everything in one data frame. We have the presences, the absences, so the presence column with ones and zeros, and all of the environmental data for our presence locations and for our pseudo absence locations. And then we're going to turn this into a spatial points layer, and I haven't included all the code here because we've done that a lot. It's the same sort of process, and it's there in the scripts. So all we're doing here is creating a presence absence file where we're a little more sure that the absences might be, the pseudo absences might be actual absences because there was more survey effort done in those grid cells. And then we're gonna fit those data to a BRT. And in order to do that, we're going to use those presence absence locations, the sort of the XY coordinates that are now a spatial points layer. We're going to use those to pull out all of our environmental data, right? And then we're going to bind all of the original data to that file. So we're going to take our presence absence data, which is, includes the ones and the zeros for each row of data, and we're going to bind it with all of the values for all 6 predictors for all of that data. So it does a lot of work fairly quickly, and then we're going to turn that into a data frame where we get rid of NA values throughout the data frame. So once that's done, we're going to use the Dismo package to run this function called GBM step. So it's drawing on the GBM package, but it does, some extra steps that allow you to sort of fine-tune your results. And so all we're doing, so this is our model object with all the amazing information that's in any model objects that's generated, and you can interrogate those on your own. I would encourage you to do that. GBM step, so that's calling our machine learning algorithm, which is essentially a BRT. So GBM and BRT are 2 sides of the same coin, really. BRT is used more commonly with this GBM step that's available within Dismo, but you can specify different families. So you could specify a Gaussian distribution for your response variable. Here we've got presence absence data. But anyway, we're going to take the data that we created in this data frame, and for our predictor variables, we're going to identify those columns. And it happens that if you look at the head of this data frame, you'll see columns 4 through 9 have the environmental variable column names that we want, and those match exactly the names that are in our folders, our predictors folders, our rasters. Anyway, we're going to use those same environmental predictors, and we're going to use that presence absence column, the zeros and ones, to be our response variable, our Y variable. Our family is Bernoulli, again, that's presence absence. Tree complexity is set to 3. That means we think there might be 3-way interactions between some of these variables. The great thing about trees is they take care of interactions automatically. They're also not terribly sensitive to missing values and all kinds of things. BRT lets you get away with a lot of things. So it's a valuable technique when dealing with noisy data. We're going to keep the learning rate at the default and also keep the bag fraction, which is the percentage of data that's used in each iteration. So we're going to keep those at the default values, and I'd encourage you to, I'll show you some places to do some more reading on some of these, but essentially we can then look at everything that's in that model object. So there's a lot of different things that are stored in that model object. We can look at the, by calling names, we can look at it all. We can look at how we called this. So if you want to, if you've forgotten somehow what that line of code looked like, it's stored in your model object. And then we can predict, just like we predicted with the Maxent model. Predict, we're going to predict into that folder, well, not into that folder, but into the variables that were taken out of this folder, the predictors folder, and stacked to form LIPE predictors. So that's our stack of environmental predictors. And we're going to use this model object to predict. And we want to type, specify that we're looking for the response. And then we're going to map it. We're going to plot it. And that's what it looks like. And interestingly, you can see that while it's still saying the best stuff is along the coast and this around this one little point where we've seen some frogs, some of this interior, it's really distinguishing between areas where it's not highly suitable, but it's more suitable than here. So it's doing some interesting things, right? It's a very different looking map, and generally you will find that a tuned BRT generally performs a little bit better than many. This call right here just gives you the optimal number of trees, and I think originally 3,000 had been the optimal number of trees, but it might have been different when I changed the extent to just Queensland. But anyway, you want to make sure you get to the optimal number of trees before you stop, because at each step you're learning more, and it usually takes, you know, upwards of 1,000 to 3,000 trees before things stabilize. And so again, you can do all kinds of things to explore that model object. Within the model object, you can use this function called GBM plot. And if you want the rug to be true, you know, it'll create this little, gives you an understanding of the distribution of variables or of data. But you can see, well, does it make sense if, as this environmental variable raises, my probability of occurrence increases? Well, you'll get that for any model you run. Does it make sense for your species? If it does not make sense for your species, if it looks ridiculous for some reason, then you're probably not using the best environmental predictors. Maybe you don't have enough data, but it's an important step in the validation process. But it does give you a sense of what the response curves look like for each environmental variable. So you'll get 6 of these popped out. This line of code plots your fitted values. This gives you an understanding of the strength of the interactions between your different variables, which is really useful. It gives you, you know, it sort of quantifies the strength of, at least pairwise strength of interactions between different variables. And then this turns, so this part of the model object, the contributions model object, gives you the relative influence of each variable. So it'll tell you how important relatively was each variable in creating your final model. And this is just turning that into a data frame. So it gives you a data frame with the relative influence levels for each variable presented. So it's a handy thing to use. Interestingly, So Jane Elith and others have done a whole lot of work on how to tune your BRT. And it turns out if you use too many trees, sometimes you'll start predicting more poorly as you fit more and more trees. You don't want to, there's an optimal number of trees that you can use. There's also an optimal number of variables that you can use. And initially, when I ran this for all of Eastern Australia, it told me to drop 2 of these variables. In this case, there's not a clear case for dropping any of these variables, really. But when you run something called GBM simplify, one of the things it does is it produces this plot. And here, this vertical red line suggests, well, you're not going to lose anything by keeping all of your variables. But if you saw this deviance going up, with the confidence intervals above this line, it's indicating that that extra variable is actually increasing your deviance. Or, so you have less of the deviance explained when you add those extra variables. So it's a really good way to make sure that you're not using too much in the way of variables. It does make an impact on how well you're predicting. So those are 2 steps that she uses: setting your learning rate, setting the maximum number of variables to improve predictive performance. You can read about that in a paper that they've written. There's also a much more in-depth tutorial on how to look at boosted regression tree results. I'm just highlighting this because often you can improve your results by taking your initial BRT and doing something called tuning, which is, these are kinds of examples of, very brief examples of. But it's something that currently is not available in the point-and-click dashboards. So if you really want to predict well and you're not predicting as well as you'd hoped, this is something you can do within the BRT environment, at least, to generate better predictions. And then I'm not going to spend a lot of time on GLM. There are books written on generalized linear modeling, but I just want to highlight that it works like any statistical method. So if you've had a stats class, we've got a response variable, our presence absence data. We've got all our environmental predictors. We know that our response variables are presence absence, and this is the data set that we're using. So these are the column names, which match those raster names in our predictors folders, right? And then again, you can run summary and the model object. So this is the model object that was created when we generated our GLM. You can just look at some basic summary stuff just by typing GLM1 and return. But if you type summary GLM, you'll get the full model, all the coefficient estimates, the errors, etc., all the things that you would expect in a statistical model output. You can also run a variable selection method. So there's forward, backward, step AIC, and this is one of the newer ones, step BIC, which is it's called a Bayesian information criterion. In this case, it performs similar to AIC, and you can make that backward, forward, or both when you specify this argument. But essentially, you want the more parsimonious model, and generally you'll get better predictions. You'll certainly get better explanation, better parameter estimates when you optimize the variables that you're using. So that's a step that's not available in EcoCommons in the point-and-click dashboards. But if you've used a lot of variables, it might be something that you want to explore to see if you can improve your results by getting rid of variables that aren't giving you a lot of bang for your buck, as it were. And then you also, so with any statistical technique, you want to look at the residual plots. Residual plots generally for this looked fairly decent, not great, not perfect, but not bad. But you do identify this really influential point, which might be having an impact on your model. So you might want to explore, well, is that a genuine point? So just like in any statistical modeling, you want to evaluate the assumptions in your model to see if those assumptions were met. If they were not, you probably need a different model, right? Or different variables. And then here, this is highlighting if we had dropped 2 of those or 3 of those variables. So we want a subset of environmental predictors that we're going to drop. So let's say the step BIC said to drop 3 of those variables. Again, that might not have happened when I changed the extent to Queensland, but it's what happened initially. But we're going to remove those rasters from the raster stack that step BIC indicated were not helping the model. So that's how you do that. You remove some, in this case, we're removing the last 3 rasters in that raster stack. And then we predict to that subset raster stack, again, using response, and we plot it. And look at that, you know, it looks like it is also predicting more into the interior of the country. And again, we haven't really dealt with bias at all in these data, so maybe that's an issue. But you can predict results with a statistical model just like you can with any of the machine learning ones, or, well, any model really, statistical or machine learning. And I don't want to spend any time on the GAMs. Again, there's been books written on how to fit a GAM. This just shows you how to call that model. So we're using the MGCV package. And what's nice about that package is that you can specify what kind of spline is going to be fit to each variable. So in this case, we've set them all to the same. But for, this is soil wetness, we're saying that our spline is going to be a penalized regression spline. So essentially, a spline sets the number of knots. So how curvy is your line going to be through the data? If it has tons of knots, it's going to be really curvy, but it's probably going to overfit the data. What a penalized regression spline does is it says, well, if those extra knots, it'll first penalize, you don't want to put too many knots in, and it'll also reduce the number of knots to 0, potentially, if 0 fits the data better. So that means for each environmental variable, you're not saying, oh, well, this is what the curve looks like. You might want to set the number of knots specifically if you know what the response should look like, right? If you know it should have 2 humps over 20 years or over this environmental gradient. Sorry, time's not a variable here. But anyway, how you set your spline can be important. Setting it this way allows for a lot more flexibility if you don't really understand your system well. This is not a bad way to go. And again, it's binomial data, and we're using that same set of predictors. We can check our residuals and look at our data. Here we compare the GLM and the GAM. and they both perform similarly, but one does a little bit better. We can plot those results. We can predict. We can predict that using that same subset that was selected in GLM. We can predict using our GAM1 prediction, right? And then we would plot GAM-pred to get this map. And again, you're seeing, interestingly, the GAM seems to be distinguishing a little bit better in these open areas than the GLM was, right? So maybe there's something to be said for that nonlinear, but that's just a visual check. We'll talk more about validation in the next module. So again, if all this R stuff is going over your head a little bit, I'd encourage you to study a little bit more about the basics of coding, and Amelia does a really good job of walking you through the data carpentry exercises. You can find that in the educational materials section of the EcoCommons website. You can also find use cases that demonstrate other functionality that is available within EcoCommons, or other examples of using the point and click environment or using the coding environment to run through various problems. If you do check us out, please let us know what you think. We'd love to hear from you. And if you're curious how things are developing, again, we're really hoping that EcoCommons will be the place that you can find more and more scientific workflows that are shared among environmental ecological modelers. And we have some really well-developed workflows now, but we've got some new ones coming: generalized dissimilarity modeling, risk mapping, to name a couple of them. And that will continue to grow over time. So I'd encourage you, if you're interested in what kinds of models we might be bringing in, time series is on my list of things I'd love to see. Just visit our website, sign up for a newsletter, follow our journey, figure out what we're up to. And again, we'll be launching to the public, so everybody will be able to use this in November, late November of 2022. And again, none of this is possible without our partners and collaborators. The people, we're really standing on the shoulders of giants in a lot of ways, and none of what we do is possible without them. And thank you for listening. The next, so we've covered a lot of ways to get results. Which one's the best? So you can do some homework and figure that out. But if you are just measuring predictive performance, we'll talk about that in the next module. How do you evaluate how well your model is performing?